Now we come to chapter 9. In chapter 9 we shall study about HANKEL transform. HANKEL transform arises naturally when one solves boundary value problem formulated in cylindrical coordinate system. Chapter 9 is divided into two modules. In first module of chapter 9 we shall study HANKEL transform and its properties. In this module we shall first derive HANKEL transform of order 0. As we have seen in previous chapters, HANKEL transform is also derivable from Fourier transform. So, Fourier transform is the mother transform. The two-dimensional Fourier transform of a function f(x,y) defined for minus infinity less than x and y less than plus infinity is capital F k L equal to double integral from minus infinity to plus infinity small f(x,y) e to the power I k x plus L y dx dy as given in equation 1, and its inverse formula is given by small f(x,y) equal to 1 by 2 pi integral from minus infinity to plus infinity, integral from minus infinity to plus infinity capital F k L e to the power minus I k x plus L y dk dl as given by equation 2. So, this Fourier transform in two dimension has been defined in the chapter where we have studied Fourier transform. Now, if we change the rectangular Cartesian coordinate system x y to polar coordinates r theta defined by x equal to r cos theta, y equal to r sin theta, where theta lies in the interval 0 to 2 pi and r lies in the interval 0 to infinity, and we also change k L to polar coordinate rho phi defined by k equal to rho cos phi, L equal to rho sin phi. Here also rho lies in the interval 0 to infinity and phi lies in the interval 0 to 2 pi. Then if we calculate k x plus L y, it comes to r rho cos theta minus phi, and also we write capital F k L when changed to rho phi coordinate, we denote capital F of k L as capital G of rho phi, and small f of x y we denote it by small g r theta as given in equation 3. So, with this change equation 1 becomes capital G rho phi equal to 1 by 2 pi double integral with respect to theta and r, where r integral is from 0 to infinity, theta integral is from 0 to 2 pi, r g r theta e to the power r I rho cos theta minus phi d theta dr as given by equation 4. Let us assume here that small g r theta is independent of theta, so that we can write small g r theta as g r. Then equation 4 becomes capital G rho phi equal to 1 by 2 pi integral from 0 to infinity r g r integral from 0 to 2 pi e to the power I r rho cos theta minus phi d theta dr as given by equation 5. Now, it is known that if J0 x is a Bessel function of first kind of order 0, then J0 x has the integral representation given by J0 x equal to 1 by 2 pi integral from 0 to 2 pi e to the power I x cos theta d theta. Now we consider the integral 0 to 2 pi e to the power I r rho cos theta minus phi d theta as given in equation 5, that is the theta integral. This integral we can write it as integral from minus phi to 2 pi minus phi e to the power I r rho cos psi d psi, where we write psi as theta minus phi. Now the integral psi integral minus phi to 2 pi minus phi can be broken into 3 integrals given by minus phi to 0 plus 0 to 2 pi minus 2 pi minus phi to plus 2 pi, and the integrand is e to the power I r rho cos psi d psi. Now in the first integral, that is minus phi to 0 d psi, here we substitute psi equal to minus psi, so that this can be converted to integral from 0 to phi e to the power I r rho cos theta d theta, plus the second integral is from 0 to 2 pi e to the power I r rho cos psi d psi, and in the third integral we substitute psi equal to 2 pi minus theta, and this integral becomes phi to 0 e to the power I r rho cos 2 pi minus theta. So in this step we can see cos 2 pi minus theta is cos theta, so that the first integral and the third integral cancels, so that we get integral from 0 to 2 pi e to the power I r rho cos psi d psi, and this by the definition or rather integral representation of J0 x given here, we can write this integral as 2 pi J0 r rho. So with this simplification we can simplify the inner integral in equation 5 as J0 r rho, and we get G capital G rho phi equal to integral from 0 to infinity r g r J0 rho r dr, and here we can see that right hand side, in the right hand side there is no phi, but in the left hand side G is a function of rho and phi. So this shows that G rho phi is independent of phi, and we can write G of rho phi as G rho. Thus we obtain capital G rho equal to integral from 0 to infinity r g r J0 rho r dr as given by equation 6, and capital G is known as the HANKEL transform of order 0 of the function small g r. Similarly, from the inverse two-dimensional Fourier transform we can derive small g r equal to integral from 0 to infinity rho g rho J0 rho r d rho as given in equation 7. Here equation 7 is the inverse formula for HANKEL transform of order 0. So from 6 and 7 we can say that capital G rho is the HANKEL transform of the function small g r, and equation 7 is the inverse transform formula. If we observe equation 6 and 7, we can say that capital G rho is the HANKEL transform of order 0 of function small g r, or we can say from 7 small g r is the HANKEL transform of capital G rho. Here the transform and its inverse transform formula, they are the similar type. Next we shall derive Hankel transform of order n. Here we shall assume that small g r theta depends on theta, where theta lies in the interval 0 to 2 pi. In contrast with Hankel transform of order 0, where we have assumed that small g r theta is function of r only. Here r and theta are the polar coordinates, then we can expand g r theta in Fourier series as given by g r theta equal to summation n equal to minus infinity to plus infinity g n r e to the power I n theta, where the coefficient g n r is equal to 1 by 2 pi integral from 0 to 2 pi g r theta e to the power minus I n theta d theta as given by equation 10. Now, in xy coordinate system, where x equal to r cos theta and y equal to r sin theta, g r theta is small f x y, where x y lies in the interval from minus infinity to plus infinity, and in rho phi coordinate system, where rho is k cos phi and L equal to k sin phi polar coordinates, capital F k L is equal to capital G rho phi, where k and L both lie in the interval minus infinity to plus infinity as stated in equation 4. Now, from equation 4, that is this expression, this equation, this is obtained from the Fourier two-dimensional Fourier transform in polar coordinate. So, we get g rho phi equal to 1 by 2 pi integral from 0 to infinity r dr integral from 0 to 2 pi e to the power I r rho cos theta minus phi g r theta d theta. But capital G rho phi has the expansion given by summation n equal to minus infinity to plus infinity capital G n rho e to the power I n phi, where the coefficient capital G n rho is equal to 1 by 2 pi integral 0 to 2 pi capital G rho phi e to the power minus n phi d phi. Then if we substitute, we get G n rho is equal to, G n rho is this. So, here we substitute instead of capital G rho phi this expression as given by equation 11. We get G n rho as 1 by 2 pi whole square integral from 0 to 2 pi e to the power minus I n phi integral from 0 to 2 pi integral from 0 to infinity e to the power I r rho cos theta minus phi r g r theta dr d theta d phi. Now, in this expression, we substitute instead of small g r theta, we substitute the expansion for small g r theta, so that we get capital G n rho as 1 by 2 pi whole square integral from 0 to 2 pi e to the power minus I n phi integral from 0 to 2 pi integral from 0 to infinity r e to the power I r cos theta minus phi summation m equal to minus infinity to plus infinity g m r e to the power I m theta dr d theta d phi. This we write as, after interchanging the order of integration, summation which is permitted we assume equal to 1 by 2 pi whole square integral from 0 to infinity summation m equal to minus infinity to plus infinity r gm r I mn rho r dr, where I mn rho r is the double integral from 0 to 2 pi e to the power minus I n phi plus I m theta plus I r rho cos theta minus phi d theta d phi. Now, we shall evaluate this integral. To evaluate this integral, we substitute alpha equal to theta minus phi and beta equal to theta plus phi. So that theta equal to alpha plus beta by 2 and phi equal to beta minus alpha by 2, where alpha lies in the interval minus 2 pi to plus 2 pi and beta lies in the interval 0 to 4 pi, and d theta d phi is half of d alpha d beta. So, with this substitution, I mn r rho becomes half integral from 0 to 4 pi d beta integral from minus 2 pi to plus 2 pi e to the power minus I n beta minus alpha by 2 plus I m alpha plus beta by 2 plus I r rho cos alpha d alpha. So, this becomes equal to half integral from 0 to 4 pi e to the power I by 2 m minus n beta d beta integral from minus 2 pi to plus 2 pi e to the power I by 2 m plus n alpha plus I r rho cos alpha d alpha. Now, for m not equal to n, the beta integral can be evaluated and can be found to be equal to 0, and for m equal to n, the beta integral becomes equal to 4 pi, which is very obvious. Thus, with this simplification, capital G n rho equals to 1 by 2 pi integral from 0 to infinity r g n r integral from minus 2 pi to plus 2 pi e to the power I n alpha plus e to the power I r rho cos alpha d r. Here we have simplified I m n and we substitute in the expression for capital G n rho here. So, this summation contributes when m is equal to n, otherwise it is equal to 0. So, in the expression for G n rho here, we evaluate the inner integral and we obtain G n rho as integral from 0 to infinity r g n r j n r rho dr, where rho is positive as given by equation 12. Since the alpha integral here can be simplified to 2 pi j n r rho. Again, from equation 3 and 2, which are given by, this is equation 3 and this is equation 2, that is the 2-dimension Fourier inverse formula, we obtain g r theta equal to 1 by 2 pi double integral from minus infinity to plus infinity capital F k L e to the power minus I k x minus I L y d k d l, which is equal to 1 by 2 pi integral from 0 to infinity rho into integral from 0 to 2 pi e to the power minus I r rho cos theta minus phi capital G rho phi d rho. Now, from equation 10, where we have expanded small g r theta, the coefficient g n r is equal to 1 by 2 pi integral 0 to 2 pi small g r theta e to the power minus I n theta d theta. Now we substitute in this integral the expression for small g r theta from here, so that we obtain an expression 1 by 2 pi whole square integral from 0 to 2 pi e to the power minus I n theta integral from 0 to 2 pi integral from 0 to infinity rho e to the power minus I r rho cos theta minus phi capital G rho phi d rho d phi d theta. Now, in this expression we substitute the expansion for capital G rho phi so as to get long expression like this. And this, in this expression we interchange the integral and summation to obtain small g n r equal to 1 by 2 pi whole square integral from 0 to infinity summation m equal to minus infinity to plus infinity rho capital G m rho j m n r rho d rho, where the j m n r rho d rho, or rather the expression for j m n r rho is the integral from 0 to 2 pi integral from 0 to 2 pi e to the power minus I n theta plus I m phi minus I r rho cos theta minus phi d theta d phi. Now, it is easy to show that j m n is equal to 0 if m is not equal to n. So, if j m n is equal to 0 for m not equal to n and j m n is non-zero for m equal to n, then this, in this summation we are left with only one term and we get g n r equal to 1 by 2 pi integral from 0 to infinity rho capital G n rho integral from minus pi to plus pi e to the power minus I n alpha minus I r rho cos alpha d rho. The inner integral can be simplified and we obtain g n r equal to integral from 0 to infinity rho capital G n rho j n r rho d rho, where r positive as given by equation 13. Thus, equation 12 and 13 produce Hankel transform of order n given by h n g r, which is denoted by capital G rho, that is equal to integral from 0 to infinity r g r j n r rho d r, and its inverse h n inverse of capital G rho is small g r, which is equal to integral from 0 to infinity rho capital G rho j n r rho d rho. Here we note that general Hankel transform of order nu, where nu is greater than minus half, is defined by h nu of f r, which is denoted by capital F rho and is defined by integral from 0 to infinity r f r j nu rho r d r as given in equation 14, and corresponding inversion formula is h nu inverse capital F rho is small f r, which is defined as integral from 0 to infinity rho capital F rho j nu rho r d rho as given by equation 15. For existence of a Hankel transform defined by equation 14, root over r f r is piecewise continuous and absolutely integrable on the positive real line. And number 3, the proof of inversion formula 15 is similar to the corresponding proof of Fourier inversion formula, but it is somewhat complicated as the kernel involves Bessel function, which are more complicated than those of the kernels of the Fourier transform. So, here we are not going into the detail of the proof. So far we have derived Hankel transform of order 0, of order n and order nu, and we have seen that Hankel transform can be derived from Fourier transform. Now we shall study some properties of Hankel transform. The properties of Hankel transform. First property is the linearity property. Hankel transform of order nu of the function C1 fr plus C2 gr is equal to C1 capital F rho plus C2 capital G rho. Here C1, C2 are constants and capital F rho and capital G rho are the Hankel transforms of order nu of the function small f r and small g r respectively. Similarly, inversion of C1 capital F rho plus C2 capital G rho gives back C1 small f r plus C2 small g r. Proof is very simple. We write Hankel transform of order nu of the function C1 small f r plus C2 small g r. This is equal to integral from 0 to infinity r C1 f r plus C2 g r j nu rho r dr. This can be splitted to write C1 into integral 0 to infinity r f r j nu rho r dr plus C2 0 to infinity r g r j nu rho r dr, which is equal to C1 capital F rho plus C2 capital G rho. Next is scaling property. Let h nu f r is capital F rho, then h nu of small f a r is equal to 1 by a square capital F rho by a, where a is some positive constant. For proof, we write h nu of f of a r, this is equal to integral from 0 to infinity r j nu rho r small f a r dr as per definition of Hankel transform of order nu. If we substitute a r equal to some constant say r, then this is converted to 1 by a square integral from 0 to infinity r j nu rho r by a f r dr, and this is equal to 1 by a square capital F rho by a positive. So, scaling property is proved. Next is Parseval theorem. Let capital F nu rho is the Hankel transform of order nu of small f r, and capital G nu rho is Hankel transform of order nu of small g r. Then according to Parseval's theorem, integral from 0 to infinity rho capital F nu rho capital J nu rho d rho is equal to integral from 0 to infinity r small f r small g r dr. This is Parseval's theorem. For proof, we start with integral from 0 to infinity rho capital F nu rho capital G nu rho d rho. This is equal to integral from 0 to infinity rho capital F nu rho, and instead of capital G nu rho, we write the expression integral from 0 to infinity r small g r j nu rho r dr d rho, because capital G nu rho is the Hankel transform of small g r. Now we interchange the order of integration, and we get integral from 0 to infinity r small g r dr, integral from 0 to infinity rho j nu rho r capital F nu rho d rho, and the inner integral by inverse of Hankel transform, we can write it as small f r. So, this gives integral from 0 to infinity r small f r g r dr. So, Parseval theorem is proved. Next, we shall obtain Hankel transform of f r by r. Let capital F nu rho equal to thus we denote it by the Hankel transform of order nu of the function small f r. Then capital H nu of 1 by r f r, that is Hankel transform of order nu of the function f r by r, is equal to rho by 2 nu capital F nu minus 1 rho plus capital F nu plus 1 rho. This we have to prove. and this follows from the property of Bessel function, that is twice nu by z j nu z equal to j nu minus 1 z plus j nu plus 1 z. Now, we have Hankel transform of 1 by r f r equal to integral 0 to infinity j nu rho r f r by r dr. Now, this j nu rho r, according to this formula, it can be adjusted, that is it is divided by rho r and multiplied by 2 nu and some adjustment is made, so that we get rho by 2 nu integral from 0 to infinity r j nu minus 1 rho r plus j nu plus 1 rho r f r dr. And if we separate the integrals, we get it as rho by twice nu capital F nu minus 1 rho plus capital F nu plus 1 rho. Next property is Hankel transform of order nu of the function r to the power nu minus 1 ddr of r to the power 1 minus nu fr is minus rho capital F nu minus 1 rho. This also follows from the property of Bessel function, that ddz of z to the power nu j nu z equal to z to the power nu j nu minus 1 z. We start with the left hand side, that is Hankel transform of r to the power nu minus 1 ddr of r to the power 1 minus nu fr. This is written as integral from 0 to infinity r to the power nu minus 1 ddr of r to the power 1 minus nu fr into r j nu rho r dr. We integrate this by parts and we obtain r fr j nu rho r from 0 to infinity minus integral from 0 to infinity r to the power 1 minus nu fr ddr of r to the power nu j nu rho r dr. Now, here we apply the property of Bessel function given by this expression to obtain that, considering that first term is 0 from the property of Hankel transform. So, this equals to minus integral from 0 to infinity r to the power 1 minus nu small fr r to the power nu j nu minus 1 rho r dr, and this can be simplified to get minus rho capital F of nu minus 1 rho. Next is sixth property, that is Hankel transform of r to the power minus nu minus 1 ddr of r to the power 1 plus nu fr. This is equal to integral of 0 to infinity r to the power minus nu minus 1 ddr of r to the power 1 plus nu fr r j nu rho r dr by using the definition of Hankel transform. Again we integrate this by parts and we obtain this expression. Again we use the property of Bessel function to obtain Hankel transform of r to the power minus nu minus 1 ddr of 1 r to the power 1 plus nu fr equal to integral 0 to infinity r to the power nu plus 1 fr into minus r to the power minus nu j nu plus 1 rho r rho dr, which is equal to rho into integral 0 to infinity r fr capital J nu plus 1 nu rho r dr, and this is the Hankel transform of small fr and this is equal to rho capital F nu plus 1 rho. So, we have so far proved some properties of Hankel transform, and we may note that there is no shifting property of Hankel transform, and also there is no convolution theorem for a Hankel transform. This is due to non-existence of simple addition formula for Bessel function. So, in this module we have learned how to derive Hankel transform and its inverse formula, and we have studied some properties of Hankel transform. With this we conclude module 1 of chapter 9.